Have you ever really looked at the shirt you're wearing? I mean, really looked? Because there's a hidden story of some seriously cool technology woven right into its threads. Today, we're going to unravel how your clothes are deeply connected to code.
So let's just jump right in with a question. What on earth could your favorite polo shirt possibly have in common with this super advanced, high-speed factory robot? Well, the answer is a pretty amazing journey that takes us from old-school threads and gears all the way to big data and artificial intelligence.
Here's the roadmap for how we're going to unpack all this. We'll start with the fabric that's probably in your closet right now. Then we'll dive into the cool mechanics that actually create it. After that, we'll see how that tech got way faster, how it's getting a whole lot smarter, and then finally we'll look at the hidden environmental price tag for it all.
All right, first up, the fabric in your closet. We're about to put a name to a very common texture that I guarantee you've worn before, even if you had no idea what it was called.
We're talking about something called a Dobby weave. Basically, it's any fabric that has these small geometric patterns woven right into the material. And this is the key. It's not a print that's stamped on top. The texture, the design, it's literally part of the fabric's DNA. And it's all made on a special machine called a Dobby loom. And trust me, you've definitely worn this. The classic example is the peak fabric on polo shirts. You know that slightly bumpy, textured feel? That's a Dobby weave. But you also see it in dress shirts that have a little extra texture, and it's perfect for checkered and striped patterns. It's everywhere, even in skirts and dresses.
Okay, so how does this actually work? Let's go from a single thread to a full piece of textile, and look at the three main ways you can weave a pattern into fabric.
All right, a quick crash course in Weaving 101. At its core, every loom does the same thing. It weaves horizontal threads, called the weft, through vertical threads, called the warp. The real magic, though, is in what's called the shedding mechanism. Its job is to lift up very specific vertical threads to create a little opening, or a shed, so the horizontal thread can pass through. The sequence of which threads it lifts is what creates the pattern. Think of it like this. You've got 3 levels of power. On the basic end, you have the tappet, which is great for simple stuff. At the super-powered expert end, you've got the jacquard, which can create literally any image. But right there in the middle, in that Goldilocks zone, is the Dobby. It's the versatile workhorse that gives you those cool, complex geometric patterns we've been talking about.
So that brings us to the main event, the mechanical heartbeat of this whole operation. Let's take a look under the hood of the Dobby loom itself.
Now, to really get the Dobby, you have to know about one key part, the heeled frame. It's just a frame holding a bunch of wires that the vertical threads are passed through. The Dobby mechanism's entire job is to lift and lower these frames in a super precise, pre-programmed order. That's how you get the pattern. Okay, this looks complicated, but it's actually a pretty genius mechanical dance. It all starts with a pattern chain, kind of like a music box cylinder with little bumps on it called risers. When a riser comes along, it pushes up a lever, which engages a gear that, you guess it, lifts the heeled frame. If there's no bump, a sinker, the lever drops, engages a different gear, and pulls the frame down. They call this a positive Dobby because it has direct mechanical control over both the up and the down motion. But, you know, old school mechanics can only move so fast. And in manufacturing, speed is everything. This led to what we'll call the rotary revolution. To keep up with demand and just get more efficient, the classic Dobby needed a serious upgrade. The mission was simple: make the loom go faster, a lot faster. The answer? The rotary Dobby. So how'd they do it? What's the secret sauce? Well, instead of all those clunky levers, it uses a clever system of latches that connect and disconnect a spinning disc from the part that moves the frame. But here is the absolute game changer. The main shaft of the loom doesn't have to stop and start anymore. It just slows down for a split second to make the pattern selection. That sounds like a tiny change, right? But it was a massive breakthrough that let these things run at incredible speed. And that relentless push for more and more efficiency brings us right up to today. This is where the simple loom gets a brain, and we move from pure mechanics to truly smart manufacturing. We're now talking about an idea called Industry 5.0. It's not about getting rid of the automation we already have, it's an evolution. The goal is to use all this amazing tech not just to be more efficient, but to create a system that's also sustainable, fair, and actually looks out for the human workers inside of it. So what does this actually look like in practice? Well, there's a great analogy from a research paper that really helps paint a picture. Imagine the textile mill of the future, operating like a super high-tech shipyard, a true smart workshop.
Inside this smart mill, you've got AI-powered cameras that act like a digital safety net.
instantly shutting down a machine if a worker gets too close. You have tiny sensors on everything, tracking the whole process so it can be constantly improved. All that data gets processed right there on the factory floor for instant responses and to protect worker privacy. And, of course, it's smarter with energy, powering down machines the second they're not being used.
But all this incredible intelligence, well, it leads us to our final and maybe most important topic, the carbon footprint of fabric and the hidden cost of making that smart shirt.
I mean, it all sounds perfect, right? Safer for workers, more efficient, less waste. But what's the catch? What's the hidden environmental price we pay for adding all this intelligence?
Just take a look at this number, 284 tons. That's the estimated CO2 emissions just to train one single complex AI model. That's not to run it 24/7 in a factory, that's just the energy cost to teach it how to do its job in the first place. That really puts the energy cost of AI into perspective.
And this chart drives the point home even harder. We're looking at the annual carbon footprint for running the exact same AI technology in 3 different places. In France, which has a lot of nuclear power, the emissions are super low. In Spain, with a good mix of renewables, it's in the middle. But in a place like Alberta, Canada, which relies a lot on fossil fuels, that same tech produces a massive amount of CO2.
So what's the big takeaway here? It's actually pretty simple. A so-called green technology, a smart factory, an efficient process, it's only as green as the electricity you plug it into. The tech itself is only half the story. Where the power comes from is what really matters.
So we've gone from the tiny textured bumps on a polo shirt all the way to a global network of AI-powered factories. The story of our clothes is clearly evolving big time. It seems the next generation of fabric won't just be woven with thread, but with data and, we have to hope, with a conscience. And the final question that leaves for all of us is, are we ready for that?